Is the sound okay to everyone? Yesterday
Yes,
I
sir.
just,
Yes,
Yes,
sir.
sir.
am I
Yes, sir.
audible properly?
Yes, sir.
Okay, okay, okay. So this all things we have discussed previously also, that there are hypothetical domain walls. So in a particular domain, all magnetic moments are aligned in a specific direction. So as this particular magnetic moments are aligned in a specific direction, this gives rise to localized magnetization, which is also said to be spontaneous magnetization. Spontaneous magnetization. This magnetization is in the absence of external magnetic field, as the number density of unpaired electrons of effective number of valence electrons. I remember this was the language I used in while dictating you. So, as the number of effective valence electrons, the number density is very high. So, there is the situation of strong effective spin coupling between the magnetic moment. So when you have a particular nucleus in accordance with Bohr's atomic model, and there are electrons revolving in different orbits. So it's the fluctuation of the electron cloud which is constantly changing, that is not constant. This fluctuation of the electron cloud, which is not constant, which is constantly changing, such that if we take some cross-sectional area, the number density, the total number of charge being passed by the electron cloud is not uniform. I is equal to dq by dt by definition. That is the flow of charge per unit time. And if this dq by dt, this becomes a function of time, that means the charge variation, the variation of charge q with respect to time t, if it is not constant, if it is constantly changing, it gives rise to current I. If this rate of change d by dt of q is not uniform, if it is not uniform, then the current, the electronic current, it also becomes a function of time t. This is all because you have to understand that electrons are charged particles. So I think I have discussed with you about this particular point, that in order to describe the coordinate of a charged particle like an electron, the coordinate, complete representation, complete representation of a charged particle is actually the productive multiplication of the space part as well as the spin part. Space part multiplied by the spin part. So if there is a pair of two electrons having the same directional spin, yesterday only I discussed with you this fact that if they are in the same direction, the situation is analogous to that of two bar magnets with poles in the similar direction. So obviously it is going to give rise to an unequilibrium state, and because of that particular unequilibrium state, those particular electron cloud, this situation is there. This magnetic field lines, there will be a change, there will be an alteration in their position. So they will try to spatially move apart. Same is the situation. So the space part, that means the Cartesian coordinate system, the similar to what we have done from our elementary class 11th level, that r being a function of x, y, and z. If the spin part is of the same direction, that these two electrons, the spin part is in the same direction. So there is a possibility that the space part, the electron spatially will try to move apart. So this is the reason by this particular concept itself, it is possible for the electrons with the same directional spin to remain there. So they try to move apart and arrange themselves in such a way that not exhibiting, not violating the Pauli's exclusion principle, these particular electrons in a localized region of domains have the same direction of the spin. So when they have the same direction of the spin, this as the current I being a function of time t. So by Wyatt-Savart law, if I is a function of time, this gives rise to magnetic field B, which is also a function of time. So as the magnetic field B is a function of time t, by Savart law. So each of these particular electrons having the same direction give rise to a magnetic field, an internal field. And this was the concept, this was the thing, this particular uh, strategy, this particular concept was used by West in his theory in the extension of the Langevins theory of paramagnetism. What he said that apart from the external field, when you apply a particular external field H to a ferromagnetic specimen, magnetization takes place through two processes. All these things are dictated to you. That is by domain boundary displacement and by the rotation of the wings. So during all these factors, as the number density is very high, so there is very small spatial region for the electron cloud to alter their position. That is, if both the electrons are in upspin, they remain in the upspin. It's not possible. That much of space is not there for one particular upspin to move to some another energy level and change its state to downspin. Point is this. So this gives rise to an internal field. So that particular internal field is proportional to the magnetization being developed in the system and is also proportional to B, which is said to be the West factor. So West factor depends upon the nature of the material. West factor depends upon the nature of the material. Nowadays, as material scientists are developing lot many type of emerging optical as well as energetic materials. So the waste factor has become very important in today's era of material scientist research. Why? Because that we can develop various types of complex materials, complex alloys, complex types of compounds, complex types of some silicon wafer, some thin films, quantum dots, quantum wells. So because carbon dots, carbon wells. So because of all these type of factors being taken into account, this factor has become relevant in today's study of material scientist research. So M equal to ms, what we have got from Langevins theory of paramagnetism, from Langevins theory, Langevins theory, from Langevins theory of paramagnetism. M equal to ms into a by 3. All this thing we have discussed. We have derived this particular expression itself yesterday. So let us put a equation number 1, where A is equal to mu m h by kt. This thing we have discussed. So let this be equation number 2. Now, as in accordance with the West theory, in accordance with the West theory, in accordance with the West theory, to make it generalized, we can write West and apostrophe with this West theory. This particular external magnetic field H, which is said to be magnetic field density, magnetic field intensity. This H changes to H plus Bm. So this Bm is due to an internal magnetic field. This can be written as H is equal to H. So you understand this is H applied plus HI internal field, internal magnetic field intensity. This is due to strong coupling of spin magnetic moments. And why there is a strong coupling? This is due to very high number density of strong coupling. Why strong coupling? Strong coupling due to high number density of effective वैलेंस इलेक्ट्रॉन। ये सारा कुछ आपको डिक्टेट कर दिया गया है और ये चीजें आप जानते हैं, ये मैंने पहले ही बहुत डिटेल में आपको पढ़ा दिया। तो हेंस इक्वेशन टू हेंस इक्वेशन टू gets modified and can be expressed as A is equal to nu m H plus Bm divided by Kp. Let this be equation number 3. So substituting equation 3 in equation 1, substituting equation 3 in equation 1, we get M equal to Ms. What is Ms? Saturation magnetization. This thing we have written. So Ms is equal to M into N, where N is the number of atoms per unit volume of the specimen. So Mn divided by 3, and now A has become nu times M H plus Bm divided by Kt. So M is equal to mu n m square H plus Bm divided by 3 Kt. Doing cross multiplication, It is 3 kT into m, that is equal to nu n m square into 8 plus nu n m square b into m. So you can copy it down. If I'm going fast, take your time. So you have m in the left hand side, see one term, and you have again m, the third term of the equation. Taking all these factors together, we can write m is equal to 3 kT minus mu n m square into b is equal to mu n m square times 8. चेक करके देख लीजिए, कहीं पर भी लगता हो इक्वेशन लिखने में मेरे से कोई गलती हुई है तो यू कैन पॉइंट इट आउट. So m is equal to mu n m square into 8 divided by 3 kt minus mu n m square into b. So this is the expression of magnetization in terms of small b, where b is the wedge factor. After this, magnetic susceptibility chi m is equal to m divided by 8. So directly these particular terms, they are denoting the values, the actual values mu n m square b. So I'm not giving any particular vectorial sign in it. So you don't get confused. It's actually representing the magnitude. This is equal to nu n m square, mu n m square by 3 kt minus mu n m square into b. So see, what I'm going to do is, at your intermediate level 12, you have come across this particular expression, magnetic susceptibility for a ferromagnetic substance, C is equal to T minus Tc, where Tc is the Curie temperature. So I can write this expression as, taking 3k, this factor as common, we can write mu n m square by 3k. This is equal to T minus mu n m square b divided by 3k. Check it out. Am I correct? I have taken 3k common. 3k common from the first term of the denominator. It was 3kt. So dividing the numerator and denominator by 3k. This is now the situation. New magnetic permeability of the medium, that depends upon the nature of the ferromagnetic material. N is the number of atoms per unit volume, that is also constant. M is the magnetic moment of each atom, that depends upon what type of material you are using. So it is not going to change during the course of the experiment. K is universal Boltzmann constant. 3 is a number. You check for this particular term mu n m square b by 3k. There is an additional factor of b. So b is the West constant, the West factor. Again, that depends upon what type of a strong coupling is there. What type of coupling is going between the neighboring spin magnetic moments, between the neighboring spin moments. That is also a constant. Can I write this equation as C divided by T minus Tc? So This is said to be magnetic susceptibility, and this expression is said to be Curie-West law. So this was the West theory of ferromagnetism. In the case of Langevins, when we haven't taken any internal field or internal coupling factor, internal magnetic field factor, yesterday only we got this expression of Im is equal to C divided by T for a paramagnetic specimen. And just by taking an additional factor of strong coupling, just by taking the factor of the internal magnetic field which is developed due to the strong attraction between the nearest neighbor magnetic moments, spin magnetic moments, the expression has transformed from chi m equal to C by T to chi m equal to C divided by T minus Tc. So magnetic susceptibility chi m is equal to C by T minus Tc. C is the Curie constant, and T subscript T, uh, C is your Curie temperature, where C is equal to mu n m square b m square by 3k. So let this be equation number 4. And Curie temperature Tc is equal to mu n m square b divided by 3k. Let this be equation number 5. So we have come across the expression of magnetic susceptibility for a ferromagnetic specimen, C divided by T minus Tc. Now I will mathematically discuss with you the condition of spontaneity. I mean the condition of spontaneous magnetization. Why? Because I remember I have also done like this only. You may have come across this. The Tc is the Curie temperature. So if the temperature of the system becomes greater than the Curie temperature, ferromagnetic material will become paramagnetic. You may have माने आप शायद इस चीज को रट चुके थे 12th के क्लास में. अब हम आपके सामने जस्टिफाई करेंगे कि ये सिचुएशन कैसे होता है, क्यों हम लोगों को ये चीज याद कराया गया कि ये टेम्परेचर टीसी बहुत इंपॉर्टेंट है. क्यूरी टेम्परेचर, अगर टेम्परेचर ऑफ द सिस्टम इससे ज्यादा होगा तो फेरोमैग्नेटिक मटेरियल अपने आप में पैरामैग्नेटिक बन जाएगा. ये क्यों बोला गया, कैसे होता है, तो हम लोग अब इस कंडीशन को डिस्कस करेंगे. वेस्ट थ्योरी ऑफ फेरोमैग्नेटिज्म के ही कंटिन्यूएशन में है. जस्ट आप एक सब टॉपिक लिखेंगे इसी के कंटिन्यूएशन में, कंडीशन ऑफ spontaneous condition of spontaneous magnetization. So spontaneous, self-induced, self-induced, or in the absence of external electric or magnetic field. So you are not giving any external energy, you are not applying any external field, still you are getting some magnetization. That is in the region of localized regions of domain. So that's why I said that condition of spontaneous magnetization is a part of West theory of ferromagnetism. It is not a different thing. It's just a continuation of it. So I think it was equation number 2 or 3 where we have modified A equal to mu m h plus b m divided by kt. This was your equation number. So before writing this, you can write from equation number 3. From equation 3, the value of A for the case of a ferromagnetic material. पैरामैग्नेटिक होगा तो बी जीरो होगा, बी जीरो होगा तो वो न्यू एम एच बाई के टी है. Then it is simply the situation of Langevins theory of paramagnetism. So all things has come into play because of B. You make B zero, it's a simple A. So AKT is equal to mu MH. Just a minute. AKT divided by mu M is equal to H plus Bm. So for the case of spontaneous magnetization, as we just now discussed, that H must be equal to 0. Since H is equal to 0, what is H? Applied external magnetic field. We are discussing the situation of spontaneity, the spontaneous magnetization. And when you apply H, that is said to be stimulated, meaning external effect, some change due to some external cause. So since H is equal to 0, let this equation be given by equation number 6. Since H is equal to 0, M is equal to AKT divided by mu M into B. Let this be equation number 6. So you understand, if H is equal to 0, then B will go to the denominator and you can write M equal to AKT by mu and B. Simple. Now, LA, or let me write it as first M by MS, where MS is the saturation magnetization. So we can write this as AKT divided by mu MB, and in the denominator MB is equal to M into N. This is AKT divided by mu N M square into B. चेक करके देख लीजिए. AKT divided by mu N M square into B. So this is M by MS, and what was M by MS by definition? Is it not equal to Langevin function LA? Now, one more thing. Try to concentrate on this. AKT by mu N M square B. So just now we have got the expression of critical temperature TC. So TC is equal to mu N M square B by 3K, since critical temperature TC mu N M square B by 3K. Just now we have got this expression. So let this be equation number 7. And I think this was equation number 5. 5. So from equation 5 and 7, from equation 5 and equation 7, we get LA, which is equal to M by MS, that is equal to, यहां पर आप चेक करो इक्वेशन नंबर 7 में म्यू एन एम स्क्वायर बी by 3k. So instead of writing in the denominator mu n m square b, क्या हम लिख सकते हैं 3k इंटू टी सी? अगर हम ऐसा लिख सकते हैं तो हम लोग लिखेंगे ए के टी डिवाइडेड बाई 3k टी सी. K cancelled. It is equal to AT divided by 3TC. So you have got LA equal to AT by 3TC. Just see, this factor of critical temperature has come into existence for the case of ferromagnetic substance. And just turn around your pages and check the Langevin function. Yesterday also we got that was equal to Langevin function LA for the case of paramagnetic material. I think it was simply equal to A by 3. That was a straight line passing through the origin, that particular curve. It has nothing to do with the LA curve. Both of them has an intersection only at the origin point. Whereas here, both the factors, applied temperature, temperature of the system, as well as the critical temperature, Curie temperature, which is a constant of the material. Why? Curie temperature is dependent also upon the factor B, and the factor B takes into account the spin coupling moments. तो ये नेचर ऑफ द मटेरियल पर डिपेंड कर रहा है. जो आयरन का क्यूरी टेम्परेचर होगा वही निकल का नहीं होगा, वही एल्यूमिनियम का नहीं होगा, क्योंकि इफेक्टिव नंबर ऑफ वैलेंस इलेक्ट्रॉन सबके लिए सेम नहीं है. तो बी जैसे जैसे चेंज करेगा क्रिटिकल टेम्परेचर चेंज करेगा. आप नंबर ऑफ एटम्स पर यूनिट वॉल्यूम को सेम कर सकते हो, आप मीडियम को सेम कर सकते हो. K is Boltzmann constant, 3 is constant, but B is not the same. B will change as in accordance with the nature of element, type of compound, type of metals, or any other factor. है ना? So let me make the curve again. That means LA by A is equal to T divided by 3TC. This is the situation. T divided by 3TC, LA versus A for a ferromagnetic specimen. So let us do the plot. We have done it yesterday also. LA on y-axis, that is equal to M divided by MS. Let this be the origin O. On x-axis, you have small a. So LA, you remember what was the expression for LA? It was cot hyperbolic A minus 1 by A. That is not going to change. Wes has only changed. Wes has only modified the value of A, not the form of the expression. That's why yesterday only I said, when I started with this theory, my first line was like this, that West's theory of ferromagnetism is an extension of Langevin's theory of paramagnetism. So let us make the curve itself. Asymptotically, it meets the saturation magnetization at infinity ms. So the curve is passing through the origin. This was the situation what we have done yesterday. LA by A tan theta 1 by 3. Up to this much we have done. And today LA by A this particular tan theta is equal to T divided by 3 Tc La by A. So there is, apart from 1 by 3, there is an additional factor of T divided by Tc. So it's how the value of T with respect to Tc that makes the material ferromagnetic or paramagnetic. Why and how? As this is the situation of ferromagnetism, so La that was equal to M by Ms. So in the case of ferromagnetism, there is a spontaneous magnetization in the system, that is capital M. That's why you have written the internal field Hi is proportional to magnetization of the material. That means, and La, this yellow curve is equal to M by Ms. So there is M in it. That means for the case of ferromagnetism, there must be an intersection in the curve at some point. It can be at this point. So there is an intersection with the point LA. Let this angle be equal to theta 1. Let this angle be equal to theta 2. For the case of spontaneous magnetization, for the case of spontaneous magnetization, this angle theta 1 must be less than theta 2. है ना? Then only, because green curve is the curve of paramagnetism. That is something which is passing through the origin. And if you make this pink curve, pink straight line at any other point, it is going to touch your yellow curve at some point itself, apart from the origin. ठीक है ना? So that's why we are saying theta 1 must be less than theta 2. Can I write tan theta 1 must be less than tan theta 2? The curve is in the first quadrant, and in the first quadrant, theta tan theta increases from 0 to 90 degree. So I can take the tan argument on both sides. If this is so, so tan theta 1 for the ferromagnetism T by 3 Tc, T by 3 Tc. This must be less than tan theta 2. That was the case for paramagnetic materials. 1 by 3. So this is the situation. 3 cancelled. So T must be less than TC. ये चीज आप याद करते थे जब आप 12th में थे. TC, this particular TC must be greater than equal to T. If T becomes greater than the Curie temperature, then there will be strong thermal agitation such that the coupling of the magnetic moments will break and they will get disaligned, disoriented, and you won't get any type of magnetization in the system. So this is the situation, this is the condition of ferromagnetism. In case if T becomes greater than the Curie temperature Tc, then there is a phase transformation from ferromagnetism, ferromagnetism, ferromagnetism to paramagnetism. A phase transition in the material. The moment this factor, external temperature of the system T becomes greater than the Curie temperature. So Curie temperature is the deciding factor whether it will be a paramagnetic material or a ferromagnetic material. So the point is this. So I hope this curve where I get this particular solution that it must intercept or touch at this point. This is clear to everyone. Like at our intermediate level, if someone asks us that what is the curve, what are the solution of y equal to x and y equal to x square. And if we have to do it in terms of a curve, what we will do is we will make y on the y-axis, x on the x-axis, and then we will say y is equal to x, that's the straight line curve, and y is equal to x square, that's the parabola. So the parabola curve will be like this. So where they intersect, that is actually the solution of the curve. The same is the same idea I have used here. That for the case of spontaneous magnetism, La, this yellow curve is dependent upon the magnetization induced in the system. And for the case of coupling, that gives rise to internal magnetization that contributes to the additional magnetization of the system that was being proposed by West. What is that? That because of the strong coupling of the magnetic moments, there is an additional internal magnetic field. So that magnetic field gives rise to the magnetization of the system. That means this pink curve must intersect somewhere in the yellow curve. At any point you can take. You can take theta 2, you can take theta 1 like this. Let's take another curve. You can take this curve. Let this be equal to theta 3. Here also it is intersecting. But again, the deciding factor is theta 3 must be less than equal to theta 1. So wherever you take any particular point, that is okay, that is justified. There is no problem in it. You can take any other angle, but it must intersect. There must be an intersection with the curve. Then only it gets a solution. So this is something that you have wrote memorized, what you have been made to learn from whatever the book you may have followed at your first level, maybe NCERT or comprehensive ABC, whatever the book you have followed, you have learned about this particular factor that TC, the Curie temperature is the deciding factor. Curie temperature is altogether responsible whether if the temperature of the system T becomes greater than Tc, immediately the spontaneous, the domain walls will break down and the system, the coupling of the strong magnetic moments will break and they will simply behave like single entities, single magnetic moments, individual magnetic moments, independent of the trajectory or the behavior of other charged lattice ions or any other type of magnetic dipoles. So I think I end at this particular point. The time is over. We are going through an online class, so I'm going through it very slowly. Okay. Rest is what again I am saying that kindly mention your complete details in the attendance sheet. It is very important. It's the record that will be calculated on your attendance. So don't like anything else. Be very formal. Properly write your